next session. So don't be confused. So the Hydrolab 4 Marientech 05 will be presented in this session as the last talk instead of the DHI 05, which will be presented in the next session as the first talk. So I hope I gave you enough time to start up the presentation, and I'm very happy that you will present now some, well, maybe not results, but I have to say that those experiments have been done very recently, so on the OWC. So I'm really looking forward what you will present right now. So.
Thank you, Mr. Chairman. Thank you, ladies and gentlemen, particularly those who are still partying into the small hours. Welcome. I'm particularly pleased here. I'm occupying a very junior role. This project was a transnational access project led by Dr. Tom Bruce at Edinburgh University. So I'm not quite sure whether I'm representing HR Wallingford as a technical director or my supervisor as a mere PhD student. I want to run, as our chairman has said, we only did these experiments the other week. So we've just got home, we've nearly unpacked our suitcase, and we've started to look inside the data. And actually our first analysis meeting happens in 2 weeks' time. So I will quickly mention a little bit about oscillating water column. You saw a little bit about this 2 days ago from our friends from LINEC, who talked about PICO. Highlight some of the challenges, a quick discussion of the GWK testing, a movie or actually only one, and then to extend what we're doing, my colleagues at Wallingford have been building some exciting open flow models with compressible air. So I think most people understand the oscillating water column. The idea is that the waves run up and down on the outside, they drive the water column, and the water column drives an air turbine. This has the huge advantage that the air turbines can be absolutely standard production devices. They also should be well away from the water, and they do not suffer from fatigue. And anyone who's worked with the reality of wave energy converters knows that there's a certain stage when suddenly the man from the steel fabrications or forgings throws his hand up as he's calculated just how little stress that he can accommodate under the fatigue loading. And anyone who's worked with real wave energy converters knows that almost always they have to re-engineer the moving and the static parts to accommodate much bigger stresses. So the big advantage of the OWC is to remove that. The disadvantage is that they're very tidal level dependent, hence the original British ones are all in a very low tidal range. And I think PICO is also relatively low tidal range. But the huge advantage, or the prospective advantage, is can we just add little oscillating water column chambers onto breakwaters that we're building for other purposes? This is in the Pacific. The actual caisson is 3 times wider than the part you see above the water. The largest caissons were 66 meters long and were installed in the Pacific. And it would not have been a big adaptation to put OWC caissons chambers on the front. So that's something that people get quite excited about. There is, of course, a number of snags behind it, but much of the engineering of the caissons is already done. This was a bold attempt, but it was, and I use the word as politicians do, bold equals frightening, because the management structure for this project was very complicated and almost certainly led to part of the disasters. And the disaster is that within quite a short period, the sea had punched right through the front hood. And many of us have our own views as to why this should have happened. There was a bit of luck, or bad luck. There was the Murphy's Law, that if you want to assure yourself of a big storm, then build something in its way. If you want to be sure the storm will not hit you, deploy 3 wave riders. So, a lot of focus on loading, but also why go into such a big, expensive flume and use European taxpayers' money to do testing? Because in the small scale, we cannot scale the elasticity of air relative to the loadings. And so a major weakness forever on all small-scale OWC testing is that the air is, relative to the wave loads, the air is infinitely stiff, whereas in reality, air is quite squashy. So the motivation was to try and quantify those scale effects and then provide validation data that we will be using at Wallingford, but we imagine other teams will later come along and seek to use the data to validate numerical models with compressible air. We did not have enough time. We did have quite a long time. I hear of some projects being talked about at this meeting that only had 2 weeks. I'm immensely pleased that Stefan and Matthias and their kind colleagues at GWK gave us 6 weeks, actually probably 6.5. We did try to be very nice, and we now know which Scottish whisky the technicians like above all others. So come and talk to me later. But we had quite a lot of time to test, and we were extremely lucky because we put together a team, some of whom had never met each other, and indeed I met one of our team here yesterday for the first time ever. But the team did work. We had a good handover, like a relay race. And what did we build? Well, this was really exciting, and this is a testament to some lateral thinking and some very helpful cooperation. And I have to say, I've said this in public before, but this project and working with the GWK team was a dream, because we stole somebody else's old caisson. We turned it backwards because Matthias or one of your technicians had spotted there was a gap at the bottom of the caisson, and if he allowed us to drill a hole in the top of his concrete, then we had an oscillating water column caisson, and amazingly it all fitted. Was it the Saltmarsh people who provided the toe slope?
Yes.
Okay, so thank you to the Saltmarsh people. Your nice 1-on-6 toe was really just what we wanted. So we did this. There were some really nice, clever ideas about it. We used the big stop log system at the front. It's not so easy to see. This is the hole, the apertures, but I move on. And you can see lots of instruments, and of course there were never enough. I will highlight one where now I am kicking myself. We should have put some other transducers in. Lots of different wave conditions. We had a very complicated, they kept insisting that they should have all the wave conditions described beforehand, and they needed a log of every condition that would be run on every day from the beginning of the testing to the end. There we have the apertures. My colleague John Alderson who has been inside here. My supervisor, Tom Bruce, what do you do with a supervisor? You always have to find something for supervisors to do, don't you? Yeah. And good PhD students always find something that the supervisor can do and not get in your way. So what we did is we sent Dr. Bruce inside here, and he painted the inside of the cells a nice white colour. Then I think he then painted your instruments white too, didn't he?
I don't know.
Oh, perhaps Matthias didn't tell you that. And then John we sent inside, and he drew some lines inside the chamber. This is the outside view. We had two cameras, one on the outside looking at the front. And I apologise, I didn't bring the movies with me, but we had a camera inside the chamber, infrared camera. I think for the first time ever, we've been able to see the water surface moving up and down during the tests. And frankly, that's been very exciting. Bit of a nightmare of a logging system, thank you, sir. It was your security camera logging system. But I put a young lady on to cutting all the film apart electronically, and now it works. So, this we call, let's see if I can make this, there we go. Now, you remember when you go into someone else's facility, you are meant to be very kind to the owner. So I just cover his eyes because what follows is quite scary. But you'll see his representative has just come into the frame to look. This is my revenge because I thought we were going to run the very first wave. It was a nice little wave of 156 millimeters. No. Secretly, his technicians set on a single solitary wave of 0.6 meter. They forgot the 1-on-6 approach slope. So by the time the solitary wave got to the caisson, it was over a meter, and there was a loud bang as it hit the roof of the... So this is our test. As John Alderson said, I think Matthias had been stung by a wasp. So this was not directly intended, but almost certainly this is the situation that caused major structural damage to the roof of the Mutriku device. So we were extremely pleased to, I think we can move on. So that gives you a picture, and inside the chamber we have the record of the camera that gets immersed. It doesn't see much when it's underwater, but it survived the immersion. So, for the boring engineers amongst us, what we want to do is, we want to say, what is the total whole body load on the caisson? Because the emphasis in many places is to build these remote, away from the land, so we have to resist the sliding load. We'll pretend that we can use Professor Yoshimi Goda's method for forces, and then we imagine that we apportion some of the load on the front hood and some on the back. And now I'm kicking myself because if we sum the load on this and the load on all of this, I'm missing the balancing load on the inside face here. And we're going to have to work quite intelligently to recalculate that. And the problem is that this is a load. It will have a water pressure, but it also will have air pressure, depending on how much we close the orifice. And so here we have quite a small orifice, and you can see the loading, and you can see the influence of wave period. And this is wonderful, nice, monotonic stuff, all utterly predictable. Phew. This gets more interesting. We suspect that good pneumatic production is in this area, but what happens if, as in Mutriku, you forget or fail to fit any control to the air? Well, you're somewhere out here, and the loads on the total loads seem to be quite small, but if I look at the pressures on the roof, probably for this case, the pressures on the roof are very high, as you just saw in the movie. Of course, if we shut the valve, you have bigger forces. So the problem is that you can limit your forces on the roof, you can limit the damage to your turbine, but do you want your device to shut completely? And this is all about control strategy. We'll feed into that later. Thank you. So, we cannot change the characteristics of the air in the small-scale model, even in the GWK. Stefan cannot allow us to use different air. So we changed the air in the numerical model. We tried to make a two-dimensional simulation, and that's quite difficult, because even in the 2D flume, the air pipe is three-dimensional. So our first version, which you'll see runs quite quickly, produced a slit, a two-dimensional slit, which is pretending to be a three-dimensional pipe. We were never very comfortable with that, but it did run. It ran very quickly, which was really convenient. So we were all set to use this as the main comparison tool. You can see now we've got the sloshing mode inside the air chamber. We've got the forces on the front, and we can calculate pressures, etc. inside. You saw there we had the high curtain wall, and we saw air ingesting. We sometimes call that belching, as air is taken in or thrown out of the chamber. It's not very efficient for production. But then Daniele Longo it was a wet weekend, he was wondering what to do. He decided to create the three-dimensional model, so he meshed up the whole one. He didn't have any agreement from me to do it. He just provided me with this on the Monday morning with a silly grin on his face. And it works really, really well. Of course, it needs more processors. Find me a numerical modeler who is not already trying to double, treble, multiply by 10 the number of processors. But you can see it's doing the same as the 2D did. It's behaving in a very controllable fashion, but the airflow is indeed three-dimensional. So, I think I will have to bite the bullet, and most of the simulations in the future will use the new Lungo 3D version. He's already used that to derive some example output from pressure transducers. Here he's comparing with the transducers that we did install, and this of course gives the huge benefit that now I can ask him to put numerical transducers in places that we forgot. It's great when you get to be old and you have clever youngsters who can fill in the gaps. So, I just turned up at the beginning and at the end and waved my hands around and was told to go and log some things. I don't think anyone used it, but the people who did all the work are in here. We have some small-scale testing at Edinburgh. We have the numerical modelling, and we have the wonderful team of Tom Bruce, John Alderson, Vincenzo Ferranti, thank you Vincenzo, Viviana Russo, and Nick Miller from Scotland. So I thank all of those, the credit should go to them.
It's okay, I think we have 2-3 more minutes. Thank you very much, William, also for well, making a preliminary feedback session, which is this afternoon. So are there any questions or comments to this project presentation? Yes, Evelyn.
So I'm Evan from MTNU. These data you were collecting, William, are they available for a Norwegian researcher or at the moment, or do I have to wait 2 years for us? We are doing similar things with another numerical model, and we are doing some tests in the IIT Madras. with a cooperation with William Sundar, and I just wonder, could we exchange some data and have an activity together?
You know the rules, you know that they become available in 2 years' time whether I want or not. I think what would be good would be to contact us. I think I already had a discussion with some of our friends at LINEC who have been doing similar, and I hope that we will be able to form a cooperation with them. It's not my project, so Dr. Bruce will be the person to make the decision. And he will be thinking inclusively. So I think the crucial thing is to explain how putting the teams together makes it stronger. I think he would be very open to that suggestion.
Thank you.
Thanks.
Yes, please.
Strongly recommended by Hyderabad that you do so, because that's literally what we're looking for, and something that we also could literally use as an example going to Hyderabad.
Once again.
It's something that's strongly recommended by Hydrolab because it's literally what we mean going to Hydrolab Plus, how to share your data. So I don't think Tom is here, but if I can give him a call, he's hesitant. So.
Okay, I think that was the perfect close-up for this presentation.